All right, I think we'll make a start. Despite the location, this isn't a keynote, so feel free to stop and ask questions. I've got a mic here we can send around. This is just a session. All right, I'm Andrew Thoelke from ARM. I'm an architect for firmware, and we've been working on ARM Trusted Firmware for a little over a year, and in public for about 11 months now. So this is a sort of third update, this time at Connect. And so I just wanted to talk a bit about what we've done since last Connect, where the software is at, and what we expect to be doing in the near future. I'll start with a recap. Discussions this week and just the interactions. It's clear that some of the teams and people who would be useful to them to understand how the architecture of the software is, the structure on the secure side, don't actually know. There's just this black box of secure software. So I'll just start off with a little recap of what the architecture is and where Trusted Firmware fits in. So ARM v8 systems, there are 4 exception levels. The lowest level, EL3, is always secure, and this is designed to provide an environment in which you can switch between the non-secure environment, where you're running hypervisors and operating systems like Linux or Android, and a secure environment where you may be running a trusted OS, which is providing secure services and has access to peripherals on the SoC, which are actually secure and only allow secure software to access them. So in ARM v8, EL3 is the environment in which we switch between those services, and we can also provide some hardware services that are best provided at this sort of highest exception level, nearest to the hardware. Because this was new software needed for v8 systems, and because it wasn't going to be a direct port from v7 software, the original monitor mode that was on an ARM v7 system, ARM decided we were going to try and write some reference code to help partners actually deliver systems with 64-bit software. One of the other challenges here is that historically on v7 systems, the firmware running in secure state was partly written by the SoC vendor, and then usually modified heavily by a trusted OS vendor in order to support their trusted OS. And there would be a challenge with implementing some of the standards coming out of ARM for CPU power management, and we wanted to make it easier for that integration as well. So I just mentioned power state coordination interface. This is a standard from ARM regarding a firmware interface for taking CPUs in and out of low power states. It's not P states, it's just the C state side of thing. And it removes a lot of the complexity for managing coherency and the race conditions involved in CPUs entering and exiting power states. The complexity is now in the firmware, but we're providing a reference implementation as open source in Trusted Firmware, and we're working to not only have a correct implementation, but over time improve its performance and scalability. We implement another standard from ARM, the SMC calling convention. This allows multiple vendors to integrate software into EL3, where that software provides different services to the normal or secure world operating systems using a standard interface. We're also using this project to provide secure configuration of ARM hardware, rather than just hoping people can read the manuals and follow the instructions there. Today, we're running on ARM v8 FVPs, so the foundation model and the base models, and also on our development board, which is Juno. It also happens to be running on some partner silicon. One of the other things we're trying to do with this is provide some reference boot flows. So again, it's for 64-bit ARM v8 systems. You could replicate these boot flows for v7. But this is about trying to combine the requirements for trusted board boot, where you have SoC has on board ROM to ensure that you can have a root of trust. At the moment, we're implementing the boot flows. We haven't got the authentication in place yet, but it allows to do secure firmware update and verified boot of operating systems while still retaining that root of trust with the boot ROM. So there's more components that you might necessarily need in an environment where you're not doing a secure boot. But the boot flow allows for runtime firmware on the onboard, on the application processor, additional processors that might be on the system, loading of secure OSs, and verification and loading of the non-secure firmware. All of the ARM Trusted Firmware code is open source. It's at GitHub. It has a BSD license, and we have a contribution license agreement, so we're happy to take contributions and feedback from partners and anybody who would like to. Just recently, we've released what we've called version 1.0, which is a bit of a jump from the previous 0.4 we released 3 months ago. And I was going to talk a bit about, well, why is it 1.0 and what's in there today. So, last time, we had most of the structure in place, but there was a lot of functionality missing. But it was enough for people to start working on it. So one of the things that we've provided now upstream is we've got a silicon port to silicon. So this is ARM Trusted Firmware running on our development board Juno. The port is integrated upstream in the 1.0 code. It has a complete PSCI implementation, or at least with regards to PSCI today. And all of the application processor firmware that runs on the ARM v8 cores is upstream in GitHub, and the firmware that is provided through the Juno builds available from Linaro comes from that source code. And you can take that source code, you can modify it, you can reprogram the firmware on the application processor. And in particular, this is the expectation that we will have the security working group here, other Trusted OS developers being able to actually do development of their Trusted OS by taking and modifying this firmware to run their Trusted OS rather than test code or as today, the firmware doesn't have a Trusted OS running on the Juno, in the Juno firmware. A couple of things we're going to be putting in place in the near future. We're going to be partitioning some of the DDR RAM so that there's more secure RAM available for Trusted OS development and porting onto V8. And we'll be taking the boot flow that we have today, but actually putting authentication stages in there. Juno doesn't have actually truly secure storage and a platform key, but we wanted it to be a development board, so we won't be able to necessarily actually have a fully secure environment and certifiably secure, but it will at least allow a lot of the software to be implemented and tested and verified to that's used in that flow. Since last time, we've done a lot of work to help implementation and integration of Trusted OSs with the firmware. And the idea is that we're not at ARM doing a Trusted OS. So in the graphic here, the ARM Trusted Firmware is the block at the bottom. At the runtime, it's the darker blue. And part of what we hope to have upstream are what we call the dispatches, which is part of the actual world switching code that's specific to a Trusted OS. So today, we've now got one of those real Trusted OS dispatches. It's the one for OPTE, for the Linaro working group. So Jens created those patches, and we merged them this week. But the actual operating system and its drivers that run in Linux, those we expect to come from third parties. So ST and the Linaro working group have been basically working on the Opti OS and its Linux drivers and its client. And that code's also upstream. So certainly today on the ARM v8 models, there's open source firmware for all of the secure software. Still to come is actually getting that ported onto Juno and having Opti running on silicon. One of the things we were working on in the models is actually since last time, we've actually introduced an interrupt model into the firmware such that the Trusted OS can get secure interrupts delivered to the OS. And there are several ways that Trusted OSs today utilize the work with normal world and secure world interrupts and how they manage those. So we've tried to build in support for various models within the firmware, and the dispatch is responsible for actually selecting the interrupt model in use. We'd love to have more of the Trusted OS dispatches upstream, particularly for open source ones, but that's still something we'd like to have done in the future, but right now we've at least got one. I realize that last statement is a bit of a mouthful, and OSS, Trusted OSS, but yes, that's a future desire. A lot of the work that we've done since 0.3 was about supporting partners into actually putting the software onto their production platforms. So we did some work on it for Juno, but a number of other partners have got quite different hardware platforms, and they've helped us to improve the flexibility and portability of the software onto their own hardware. So in particular, the boot flows that we've had in our graphics are one way of doing it. On this slide deck, they show what Juno does, but there are other ways of solving this problem. Partly, some people have their own secure bootloaders, whether they're running on the application processor or running on a secure code processor, and we wanted to support partners being able to use that. Some partners actually load the firmware into RAM before resetting the application processor, and so we wanted to make sure that was a viable option with Trusted Firmware. And in order to support all of these, we wanted to ensure that the interfaces in the boot flow are stable within Trusted Firmware, so that there's no coupling between updating the secure boot firmware and the runtime firmware. So you can take a new version of the Trusted Firmware BL31 component, and it works with your existing, with the previously written boot firmware. We've made it easier to at least initially identify what's going wrong if you've got a problem in the firmware, particularly fatal errors at EL31. So we've got some crash reporting of CPU state. One of the issues with the previous software was that it wasn't very flexible about how the software was being run in Securial 1, or even how the normal world firmware was running. And we've made it much easier and more reliable to select the execution state and register width for this software. So actually configuring the firmware to run for your particular platform is much easier. And we've had contributions from partners to help with platforms where the I/O addresses are much wider than 32 bits. And the existing memory map library we had was a flat map, which gets very large, and page tables get very large to support those devices. So we've had contributions to allow for a memory map which is not identity mapped. And within ARM, we've had our CPU teams telling us that our sequences of code for particularly resetting and shutting down the CPUs and the clusters wasn't quite following the manuals. So we've introduced some frameworks to actually provide fully correct sequences for ARM CPUs, and a framework that allows additional other implementations to be supported in the same way. Some of the things we're looking at for the future, maybe near term, some of them more longer term, is now we're running on hardware, is to do a little bit more on performance investigations around some of the important behaviors of firmware, and also looking at its scalability to larger systems. And that's partly looking to an environment where we would like Trusted Firmware to be software that's working in both enterprise and networking systems as well. Those add additional boot flow scenarios. They have different ways of bringing a system up, partly because there are additional processors often on the SoC or in the platform that can be involved in this. And also taking account of the fact that we're not just targeting this at SoC vendors and Trusted OS vendors, but ultimately OEMs are going to have to integrate software onto the platform, and making it clearer how to separate the code and integrate that code together. And the final thing I'm going to talk about that we've done in the last 6 months is we've worked at shrinking the software. So last time I was at Connect, if you built the software for our foundation, one of the FEP models, if you included our test secure payload, which is the replacement for a Trusted OS, our total RAM footprint was 292K and 24K of ROM, which was the code for the initial bootloader, BL1. 3 months later, we shrunk that to 208K, particularly shrinking the early boot stages and removing stacks they didn't need because they weren't multi-processor, and enabling the compiler to remove unused code and data. And then we've done a lot more individual pieces of work going into version 1.0, and we've brought that footprint down to 128K. In practice, you can actually make it smaller than that because not all of these boot stages are running concurrently. If we arrange the code right, we could have BL3.1 and the shared memory only using 60K of RAM, leaving the rest of secure RAM on the device available for the Trusted OS. That was a series of multiple steps. There's still some more improvement that could be made, but if this graph could be projected into the future, by the time we get to the next Connect, there'd be no firmware left. But I don't think we'll manage that. But at least it gives us some room to add some new features. So looking forward to next time we're at Connect, and what will Trusted Firmware look like then? ARM's working on reference implementation of Trusted Board Boot and authentication of images up to the non-secure firmware. Whether the non-secure firmware then carries that on with verified boot right up to the kernel and user space is subject for other teams to work on. And it's something that Linaro is working on in UEFI at least, and potentially elsewhere. There's a specification update in progress at the moment on PSCI. It'll actually finally reach a 1.0. There's some changes and additions. We expect to be providing a reference implementation of that. What else is there? Well, there's things that we might work on, but it depends on us knowing what matters most to the people who are using Trusted Firmware. So we need to know what's broken and what's missing to help you work with it on your platforms or for your use cases. But we don't just want you to tell us stuff, we'd quite like to have the code. Contributions are always welcome, so please send us patches. And the other thing I'm looking forward to is by next Connect, we'll have Trusted Firmware running on what I call real silicon, not just our development boards. But on some of the members here will have hardware platforms, and we hope to know that Trusted Firmware is running on that, and to find out what the plans are for moving forwards. That's all I had to say. I'm quite happy to have questions. And I'm not Mike, so I should probably say it here.
Yeah, I had just a general question about actual update of the Trusted Firmware while it's out in use. Is that supported? Will that be? Will you be able to do that?
So you're talking about updating the firmware.
Yeah.
So is this?
Yes.
So on Juno, you can actually provide a replacement of the BL1 and the actual firmware package when you boot the board, and that's possible to do even in Lava systems. And we've worked out how to do that. I think there's some improvements coming along. In production systems, the plan for the authenticated boot is not just to provide a reference for authenticated boot flow, but to actually provide reference code for authenticated firmware update as well. So that will obviously involve actually more software components than there are today, because you'll have a separate, an alternate firmware update component that isn't your standard BL2 bootloader. So that's part of the actual sort of reference specification, the trusted board boot specification, and yes, we will be providing reference code. We'll first start with the authenticated boot, but we will move on to secure firmware update.
I have 3 questions. One is, in the build system for trusted firmware, have you discussed or given a thought to including a platform hierarchy? I guess for a particular silicon vendor, if there are related platforms that they want to port the trusted firmware on, there are quite a few common components, right? I mean, right now there is, it's sort of flat, and every platform that you port it to will be sharing a common, I guess, location. But having at least one more level of hierarchy, I was thinking, makes sense.
I didn't quite catch all of that, the question there.
I guess
Sorry.
what I'm saying is, if I look at the trusted firmware build system right now,
yes,
right, there is one common place, and all the platforms basically share that common code. And I was wondering if it makes sense to have at least one more, I guess, hierarchy, one more level in hierarchy where a particular silicon vendor, if it has related platforms to share components within.
Okay, yes. So this is about not assuming that every platform is entirely distinct. So this is something that I kind of hinted at with the fact that in practice, you need to port it to an SoC, and then actually there's some of the software that needs to run is actually going to be OEM outside on at the platform layer, but not within the SoC. And your comment is actually even within the SoC, partners may have a family of SoCs which share a lot in common, but
exactly,
a difference. Yeah, we've dealt with that on our FEP models because we wanted to make it easy to use the models, that we've actually put that variation within the binary, so it's runtime variation. But it can see that maybe a build time variation would be very valuable. So we're thinking a bit about how we structure that. Obviously, because it will be to some degree within the platform layer code, it's going to be more about providing an example of how we do that. There's no requirement to follow that, but and we don't really mind how partners structure their platform code. We haven't quite solved the problem for ourselves yet, but it's a good point, and it's something that's it's an area of recognizing that there are sort of layers of porting, and it's not just one.
And the reason why it becomes sort of important for having it in trusted firmware Git repo is next time when a partner is merging or syncing to the tip, right, all the same changes will have to be sort of redone.
So we aren't averse to the idea of having more platform ports upstream from partners, but it's entirely up to partners and members whether they are going to actually contribute their ports, or even some of the common parts of their ports. So that's kind of out of our hands, but
BSD 3-clause license gives the partners flexibility of not
indeed.
having to
So partners have the flexibility to contribute or not.
Yeah. Another question was, you mentioned for things to come, more trusted RAM. Is that a requirement that that's going to be imposed on a particular platform, or I guess?
No. So this was actually just something we're doing on ARM development platforms because it's not inherent in ARM trusted firmware, and in fact the runtime component doesn't need as much RAM as it usually doesn't need a significant amount of RAM. But this is more about being flexible for particularly trusted OSs, depending on what you're installing, whether it's a small bit of secure software that the SoC vendor has themselves, all the way up to some of the commercial or open source trusted OSs, which quite like to have 1, 2, 3 megabytes of secure memory, and potentially future use cases might want more when you start looking at transferring data from normal world to secure world. So this was really about saying on our development platforms, the FEPs, and on Juno, we actually want to just allocate a significant amount of memory. So on Juno, it'll be nearly 16 megabytes of DRAM. We'll actually mark it as secure, which means that Linux can't access it. And that's available for Trusted OS developers to actually put their Trusted OS or some of their data so that they can explore use cases on Juno and not have to modify the firmware just to get enough memory marked for secure use only.
And the last question was, again, I think it's one of the enhancements, reset to RAM firmware. Is that, I guess, I haven't looked at the tip recently, but if I recall, right, there were basically two I/O methods that were supported by boot stages to load images, right, the memory map and FIB-based. But in either case, right, we were moving images, right, from one location to another. Is there an option to assume that you mentioned, right, some of the partners have boot processors that may actually load this firmware into their destination, I guess, desired locations? And then is there a thought, or is that already implemented, that the boot stages within Trusted Firmware don't move these images, assume that they are preloaded at the right place?
So that the reset into BL3.1, this was so supporting a platform where a secure co-processor actually already had the functionality of being able to load all of the firmware into RAM. And so in this case, it could load the actual EL3 runtime firmware into RAM before the application processor is actually brought out of reset, and it's just directed straight there. And the big difference is that the sort of reference boot flow with BL1 as BL1 is the reset vector, and it's in ROM. And so the first job it has is to determine whether it's a warm boot or a cold boot. In the warm boot case, we'll then actually the platform code is responsible for ensuring that reaches an entry point in BL3.1. Relevant to the CPU boot case. And in a cold boot, it will go through the whole boot flow of loading BL2. But on some platforms, there is no boot ROM for the application processor, so you need the reset handling code actually within BL3.1, and that's what we've that's that optional configuration. At the moment, it's BL2 that is responsible for loading most of the runtime firmware images, and in its present incarnation, the addresses it loads to are static. That's what the upstream code depends on. That's something that could evolve in future as we see and understand the requirements better. But that's the current code.
Thank you.
If I understand this correctly, as soon as you run Trusted Firmware, you can't give access to the FAQs to the operating system. Is that right?
Sorry, repeat again. As soon as you run,
if you run this, like if the operating system isn't running in secure mode, you can't have access to FAQ. So we have things like the FAQ debugger that people are working on, and I just wondered is there a way to pass this through to the OS, or alternatively, is there a way to have a GDB stub included in the Trusted Firmware so we can debug the operating system? Because that seems like a really nice use case if you already have the Trusted Firmware, just as a developer build that you can optionally enable something like GDB stub the way we have in QEMU.
So, right, yes, certainly with the ARM interrupt controllers that are available in platforms today, it has notions of there being non-secure interrupts and secure interrupts, and those are typically mapped to IRQ and FIQ, the physical interrupt vectors. And if you are doing things with secure interrupts, you will actually have them routed, that they will actually be routed to secure EL1, and they will arrive as fixed. Now, the firmware can actually decide to hook those interrupts into EL3 or not. So if you don't actually require those interrupts in your trusted firmware, so you haven't got a secure OS that needs interrupts, then without changing the behavior of, you can set the processor up not to trap interrupts out of normal world. I would need to go and have a look whether you can actually configure the GIC to allow physical FIC interrupts to be managed by non-secure software. It's also possible to have, when the FIC interrupts are being taken in the secure side, to try and work out how to essentially then provide some kind of proxy within the trusted firmware for this service, without it actually having the physical fix being handled by the operating system. There are some challenges with secure interrupts because really they need to be owned either by the trusted firmware EL3 or by the secure OS.
Like all of them at once, or
all of the secure interrupts have to be in one place or the other because the interrupt controller doesn't consider there being two different interrupt targets, and software can solve the problem and say, well, let's separate interrupts and have some handled in one place, some in the other. Doing that generically is difficult because it defines an interface between the trusted OS and trusted firmware that doesn't exist today. So future hardware platforms and future interrupt controls will make that easier. But today, there's probably a number of ways that you can provide something which may come close to solving your needs. But I think it's probably a discussion to sort of draw some pictures and see what one works for the particular setup.
Right, so if we were to have a GDB stub in Opti and move the interrupts there, does that already have an interface to look at the register state of the non-secure OS?
No, it wouldn't.
Is that a thing that's hard to add?
Most of that register state is saved in memory in trusted firmware. So given Opti has got its own dispatcher code, which basically is providing services to Opti, you could provide basically work on both those components to actually provide that kind of facility. Or you could provide a facility where Opti will take the interrupt, recognize this as being the interrupt for the FIC debugger, and actually then pass control to an EL3 component to actually process it before handing control back. The challenge with the interrupts is that one environment has to take the interrupt, and if it knows it's for the other environment, you have to define a protocol for doing that in a way that doesn't result in reentrancy issues and other potential messy scenarios. We can probably talk elsewhere and so maybe draw some pictures and see what might work.
Okay. Well, I think you answered my questions. Thanks.
So, well, EL3 being the most privileged mode on the platform, I was wondering, I mean, the security of all the platform is then relying on the robustness of the ARM trusted firmware. I was wondering if there had been any vulnerability analysis that has been conducted or being planned.
So today, the software is released under BSD license. So there's an element of saying it's not possible to certify the software anyway on its own certification. If you're going to do it, it has to be the whole system, and it depends on what you do with the software. We are also going to be thinking about how we make sure we're looking at issues where we're making it more resilient, and clearly just fixing bugs is also important. If you discover things that you think need to be fixed, we're happy to have not just take a public report on GitHub, but if you want to tell us in confidence, that's also fine. There's no current mechanism in place for reporting this, other than the existing communication channels with email to. Okay, so thank you.